This conference will now be recorded.
Hi,
Okay.
everyone. Welcome to the HLD discussion today. Today, Google is going to walk us through three HLDs about the pins. The first one starting from Ramin. Ramin, you can take away. Thank you.
Thank you. So I'm going to present the first HLD. It is about response path and app state DB. What is it and why do we need it? So when we try to integrate the P4 SDN support into SONiC, we found like two problems. The first one is that like P4 is a RPC based protocol, like it is synchronous, that we send the controller send a request, it expect a response, and it expect that whether the request has been successfully committed or not, like this need to be indicated in the response. So we found that there's like the SONiC is kind of using this consistent like eventual consistency model, that there isn't an obvious way that for an application to get the response, like to see if the program that they write to FTP has been successfully programmed into the hardware or not. So this is one of the features that is lacking in SONiC. The second one that is lacking is that there's no like real state DB for the application to query the system like status. Like today, like the FTP is mostly intent basis. Like the occasion will keep trying to fulfill in best effort of the tables in the FTP, but it may not be like successfully committed into the hardware. So whatever in the FTP might not represent the real system status. And the existing state DB like it just doesn't have enough information as in FTP. And finally, in synchronous mode, like ASIC DB can represent the real hardware status, but the schema is just not really for high level application. It is very low level. So overall, there isn't an obvious way for an application to query what are the flows that have been successfully programmed into the system. With these two issue, we come up with the response path and app state DB feature. So here's the overview. We will add the notification channel from the occasion to the application just to notify the response on every request, to indicate whether it has been success or failure. And we introduce a new DB that represent the real system status. We will go into detail later. So this is the overall architecture. The black color component are the existing SONiC component. First, we have to we have to enable the sync mode. Right, this will enable the response from sync D to occasion. And the dotted line means is like a conditional operation. When the sync mode is enabled, sync D will update the ASIC DB only after the program has been successful. So here the red one is our new introduction. So first we will add the notification channel from occasion to the application. This is just using pure Redis channel. We will go into detail more. To this, we will encode the message of the response message of success or failure. If it is failure, what are the reason, etc. And if it's a succeed, we will write like the request into the app state DB to indicate, this flow has been successfully programmed. And if it's a failure, you basically just no up here. So that's the overall architecture. And any questions so far? Okay, let's move on then. So dive in a little bit detail on this notification channel. So is this red arrow here? So what? How do we how do we do it? It's just purely Redis channel. So SONiC already have like existing API for utilizing the Redis channel. Is this two API here. So in this two API, it define like the structure for those API include like a certain field, like the key, operation, and some field value pairs. So we need to define the schema on how to encode the message using this API. So first, we need to define a channel name. So this is the schema for the channel name. This table name is the FTP table name. So every table in FTP, we will have a corresponding response channel. So so far so good. In the message field, this is how we encode it. The key is the exact same key in FTP, and the operation is the status code, is the string representation of the status code. We will go into detail later. Here are the status code. And field value pair is the exactly same as the field value pair in the FTP request, except with one exception. The first field will always be this error string, and then it will the value will contain the error message. If the status is error, if it's success, this can be empty. So this is how we utilize the existing API to do this notification channel. So there are some like corner case that just the application need to be aware of. I will quickly go over this. So if the application write if multiple application write to the same DB, then they will subscribe to the same response channel. So they just need to be aware that which response is for them, not for the other application. The response has include the key and all the fields. So they should be able to distinguish their request and their response. So one application might write to multiple tables. In such case, they will need to subscribe to multiple response channel if they need. So application just need to be aware when they receive a response, need to figure out what table it is for. And it is not recommend to send the multiple requests on the same key in a batch, because of the limitation of the FTP API. When the occasion get a batch, it might aggregate together if it's on the same key. So with response path enabled, it is recommended if you try to modify the same key and just do it once at a time, send the request, wait for the response, and then do the next operation. Otherwise, if you send too fast, it will be aggregate. The two requests will be aggregate together, and it might be confusing when the response come back, because it's an aggregate response. And yes, it should wait for the response with a timeout. It should not wait for indefinitely. So the last one doesn't apply to P4 but it was a good point brought up in the previous meeting with Microsoft. So when the request is partially programmed, if the request fail but it's partially programmed, in the response channel, we don't we will indicate it's a failure, but at least in the current schema, it doesn't it just doesn't have a fine-grained detail on what which attribute succeed and which attribute fail. So in such case, if the application is interesting in the exact detail, it will need to query the appstate-db. So moving on. So here's the status code we define. It is basically exactly as like gRPC status, almost one-to-one mapping. If the arrow is returned from SYNC, it will be encoded inside. So here is our mapping. So those side arrow will map to the corresponding the high layer status code, and anything else will map to unknown. This arrow occasion the arrow returning from SYNC can be one scenario, but if occasion, like occasion can also do validation check. If it fail, occasion will just directly return like some status code, for example, like invalid parameter. So now go to app state DB. So how do we do app state DB? We will use a new Redis namespace. First the most important one. It has the exact same schema, same key, same schema as FDB. Because of this, we have to use a different namespace. Otherwise, it just it just need to use a different namespace because it has the same key as FDB. So so the what's the operation on this? It's quite simple. If the request is successful, we write to the DB. If it's not, then no, we don't write there. So this DB will reflect the true system status. So any application you can just read it or subscribe to this if you are interested in knowing what the system is doing. So some corner case, if it's halfly committed, then this the app state DB should also reflect the halfly committed status as well. Currently, this is not the case in P4. But in general, if you want to implement this, that's the recommended way.
So Ranving, here I have a question.
Mm.
So when you write into the app state DB, right, you will write all the contents, basically whatever we get in the application DB, including fields, you will write into the app state DB, so that for which fields the operation failed or successful from syncd, correct? Or just the
Yeah,
keys? You'll just use the keys, or like the other fields will also be written into the application state DB, the
yes.
status.
So if we the last one here is that like if the whole request is successfully like programmed. So we will write exactly, so this app state DB should look the same as FDB, right?
Okay. Which means
But
including fields, not just the keys.
yeah, it include fields, not just key.
Okay.
Like in this, like in some scenario, right, when some of the attribute get programmed but not all,
Mm-hmm.
then we better to just write the successful program one.
Okay.
So in a good case, like everything work, then the apps database should look exactly the same as FTP, but just in the failure case, it will not. So we don't use any API for this, just Redis hash. That's what we do. So a little like like point on the P4 auth. Just the since we mainly do this feature on P4 auth so far. So there are some key difference in P4 auth than any other auth. The first one is it doesn't retry. The second one is it tried to handle each request automatically. So these two, like with these two like characteristic in P4 auth, we it can integrate this response path and apps DB really well.
But some of the dependencies are satisfied with the retry, right? How do you basically handle the cases where you have the request and then there is a dependency for that request, right? And you are basically trying it, putting that keeping that message in the queue today, right? If you
Yeah.
don't retry, what will happen to those dependency
Yeah,
problems?
that's the existing occasion will do retry, but we don't do that in P4. If it's missing dependency, it will just return error.
But the P4 also depend on the data already available in the SONiC, correct?
It depends on port sort and
Okay.
maybe VRF. But like we rely on the controller to handle this dependency.
Okay.
Like
This is
like we
something like for the configuration that you are sending, and it's independent of the existing SONiC configuration. So that time you will basically you don't retry. Can I take it that way, or
we will never retry in P4. Yeah, that's how we implement this. If it is missing dependency, we will return like this error code. Like okay, something is missing to the controller. Then it's up to the controller to figure it out. Yeah, like if we do retry, it just doesn't fit well with response path. You cannot like send a response on every retry, right? So
Yeah,
yeah.
I understand that. I mean, there are, the as per the other review, right? There are, I understand that there are other dependencies with the SONiC configuration. For example, be it port creation and other stuffs, right? There are some dependencies with the existing SONiC configurations. So
Yes.
if
Yeah.
you send some P4 programming request, and that depends on the configurations already present in the SONiC, right? If that something is not there, then we should retry for that particular case, because the controller may not know whether that particular information is already present in the
So,
P4 org or not, sorry, the ARC agent or not, right?
so Venkat, P4 runtime takes care of the dependency in the sense that if we
Okay,
wait for the ports to be created
okay,
before we send any request to P4 org.
okay. So you are making sure of that, but things are happening in the DB, and we don't know at what time the ARC agent will process those events and stuff like that. Hope you are handling those cases. So
Yeah, we wait for the complete
okay,
for the successful creation before we
all right.
start sending.
Thanks, Kishan. Okay.
Yeah, now we have response path. Like if it's a P4 dependency, we know if yeah it has been programmed or not. So yeah, finally, this is optional. Like application we remain any other DB as untouched because we are introducing a new like two new component. So the app DB will still remain as like intent based kind of DB. So if a request fail, then application can choose to like clean up the intent in app DB. So I'm not going over details. So there are a few cases that how it can fail and how it can clean it up. This might be useful in one pool, um like you don't want that fail entry will be retry again after the one pool. So it just an optional operation. So some flow diagram in the successful case, application will write to FTP all the way down to the hardware ASIC, and we will have a when we enable sync mode, we will have a response from sync D to occasion, and then now with the new notification channel, we will send it back to the application. Yeah, in the P4 case, the P4 app will send back the RPC response. So the whole flow is synchronous. So in the failure case, the failure can happen in multiple layers, like in occasion, single or hardware. When it fail, the failure error code will be sent to the application, and P4 will can just indicate that in the gRPC response. So this is the first block is a failure in the occasion. The second one is in SAND, and finally in hardware. Yeah, it is shown in the batch case that application can write very fast, multiple requests very fast. Then occasion will receive them all at once. So again, it's recommended if you do it in batch, don't modify the same key. Yeah, otherwise the response will be aggregate and the application might be confused. So each of them will be handled individually and will have a different response. So yeah, this is the flow. So finally configuration. We have some opinion that not every single table or every single occasion we need this. So we will introduce a config file in JSON, like this, the blended format in JSON. We just put in the app DB table name. Like if you want to enable response, the response path feature, then just put your table name in this file. And if you want to enable the app state DB, then just put the app DB table name. And I think that's it. Yeah.
No, why do we need that configuration? Why do
Is
we
there
need this?
this just if you want to enable or disable for a particular table,
Mhm.
then you can do it here.
We can
This is in
control that in the
response.
ARC agent itself, right? I mean, why do we need an explicit configuration for that?
I think this is.
I'm sorry, I missed it. Can you repeat your question?
No, I mean, we can control that in the ARC agent itself, right? Like for which table you are, putting into the application state DB and stuff
Oh
like
yeah,
that.
that will be pretty hard coded, right? Yeah. Today we do it in P4. Yeah.
Okay.
So,
I don't.
so Venkat, just to clarify on that question, this is actually in response to a comment we received earlier. So
Okay.
our current implementation has a hard-coded, does the response for all the P4 runtime tables.
Mm-hmm.
And we received a comment in an earlier discussion that can this be configurable? Can responses and this is also something that we eventually find an application state or a response database being useful for other applications also, local applications also.
Right.
So as we carry this forward to the main orc agent and other SONiC applications,
Mm-hmm.
the idea is to enable this feature, in other words, through a config file.
Right. I mean, if we are fully migrated to the application state DB, then we no longer need this configuration file. Is that correct? Or we will still keep this configuration file to look up, each and every table programming. You will look up this application state DB tables and see, okay, this table, needs the response. Then you will write into the application state DB. Is that correct?
That is a good point.
Yeah.
This level of configuration is probably needed only as we are in the migration process.
Mm-hmm.
Once this is available across all applications,
Mm-hmm.
it can be a single config saying, does the system need responses or not?
Right.
Right now, it is on a table by table basis because the P4 tables have it and the other tables don't have it, and things like that.
Okay. Okay.
But eventually, we should be able to make this large config into a single option.
All right. Thank you. Thanks, Bhagat.
Any further question? If not, I think we can move on to the next HOD.
Sure. Give me one sec. Make. Yeah, Kishan, can you try to share your screen?
Yeah.
Awesome.
Okay. I hope you're able to see my window.
Yes.
Okay. So we are going to look at the changes done in packet IO for pins. So we'll start off with the requirements. For P4 runtime, we have a couple of unique requirements that we felt need some changes in the packet IO path that is different than what SONiC uses. So in SONiC, we use the netdev ports, and what we get in the packets are basically just the input port, basically based on the netdev port where the packet is received. That is the input port on which the packet came in, and we just get the packet, the payload. But for P4 runtime, we basically also we need some additional information, like the target egress port. So this is basically the port that the packet would have been forwarded if it were not trapped or copied. And we also need another requirement in the sense that we are not interested in other punt packets that the SONiC application might have installed the punt flows for. Like, for example, if there is a local LACP running, or if there is some other local applications that have installed the punt flows, then we want the P4 runtime to receive packets, the packet ends for only the flows that the P4 runtime installed and not everything else. So those are a couple of unique requirements on the receive path. And on the transmit path, the first one is pretty straightforward, and it is the same as what regular SONiC uses, in the sense that we want to send a packet out on a particular port, and we can use the NetDev port, create a socket, and then write on the socket to send it out on the particular port. There is also another requirement called the submit to ingress. So this is basically leveraging the ASIC's switching pipeline to forward the packet out. So in this scenario, we do not know the specific port on which the packet needs to be sent out. We just have a packet that needs to be kind of injected into the switching pipeline, and then whatever flows are programmed on the ASIC, the packet will basically use those to find the appropriate output port and then send it out. If it cannot find anything, then it'll take the usual action like a drop action or whatever is the default action to be taken. So given these receive and transmit requirements, so we'll first look at the receive path. So as I earlier mentioned, the requirement, the first requirement on the P4 runtime is basically to isolate the punted traffic that is specific to the flows installed by P4 runtime. So how do we do this? If we add a capability that the application basically sends a unique identifier or a context value that it can send to the ASIC along with the flow that it is programming. And then if the ASIC can add that attribute in the packets that are punted, then in the receive path, we can basically use that unique identifier to isolate the traffic between the punt flows that were installed by P4 runtime and other applications. So fortunately, Sai provides such a capability in terms of the user-defined traps and the host interface type GNetlink. So we can basically use these to program the ASIC when the main idea is like what we just looked at in terms of when the application will use a user-defined trap, and then instead of sending the packets on the default NetDev port as the host interface, now we program the host interface table to basically say that for all the user-defined traps that I'm using, send the packets on the host interface type GNetlink on the specific GNetlink family name. And once we program the host interface table, then the packets will basically come with the special identifier. And then we have like a certain new function written in the receive path that will look at the packet metadata and then identify the tag. And then we also have a new a generic kernel module that is written that basically packs all the packet attributes that we need. For example, the ingress port on which the packet came in, the target egress port, and any other new metadata that we might want to add. And then the packet payload, pack all of those things, and then send it on the GNetlink socket. So we need these attributes because this is coming on a regular like a GNetlink socket rather than on a per port specific NetDev port. So that is why we need all these attributes, including the input port on which the packet came in. And so this model is like again leveraging on the existing host interface type GNetlink, and it's already used by SFlow in SONiC. So we are kind of leveraging some of the infrastructure that is already available over there. And so given the kind of the high level flow that happens here, so how do we kind of define these the unique attribute ID or the unique context values? So what we chose is basically the CPU queue that is used for the packets to be sent when the punt when the punt packets arrive. So the gnetlink name and then the family name and the socket name, everything is specified in the cop config JSON file. And when p4org initializes, it basically creates a user-defined trap for each CPU queue. So since, for example, if we have 8 queues, then we define those 8 queue attributes, something like this here. For each of the queue, we specify the gnetlink name and the multicast group name. So p4org, when it initializes, it creates a map of the user-defined traps for each of the queue. And when p4 runtime sends a particular ACL entry to be installed in the punt, then it basically looks up at the CPU queue that comes along with the request, and then looks up the map and then finds the particular user-defined trap and uses that user-defined trap to program this ACL entry. And so that kind of covers the end-to-end flow, and we will look at what are the changes that are required. So
Kishan, one quick question.
Yeah.
So when you define the COP configurations, right? So there are predefined COP queues for certain protocols, right, to trap to CPU, and you will be like using the new CPU for these kind of packets, or like you will. Wow, how are you basically writing that COP configuration? Can you give more information on that?
So the cop config today is basically just mapping for each of the CPU queue. We basically specify what is the gnetlink family name. So in our case, basically we are just using the same multicast group name, right? So what it essentially does is it basically maps all of these. It creates these 8 user-defined traps, and then every time when an ACL entry comes, based upon the specific queue for that ACL entry is to be programmed, it picks up the specific user-defined trap. So we specific to your question, like it really is up to the controller. For example, the controller might say that ARP and DHCP packets should go to CPU queue2 and things like that. And if there is local applications that are already using, like for example ARP, then that we do not touch that, right? Like meaning that goes on the regular NetDev port, and these packets. So of course we are basically making the assumptions that any conflict between an existing punt and what the controller might have to install is kind of resolved outside of this, right? Like meaning we have to make sure that there is no conflict, or if there is a conflict right now, we don't have a mechanism to handle it, or we don't still see a use case where the same type of packet needs to be punted to both the controller and to a local application. Of course, in the future we might receive, or there might be some use cases for others where such a scenario might come up, and we have that in consideration. We have some ideas on how to resolve that, but it's still not complete, and we will address that in the future.
Okay, all right. Thank you.
Okay. Again, coming back to the changes that are required. So in the receive path, as we kind of briefly looked at, there are 2 paths to it, right? Like one is the new module that basically will pack all the packet attributes and then send it on the gnetlink socket. So that is a common piece of module that any vendor can use. And there is a second part, which is basically looking at the packet metadata and then identifying the context value that the application put in.
Kishan?
Yeah.
One quick question regarding the COP, right? So are you adding entries to the COP J2 file as such?
Yeah.
So that would be installed for kind of any system, right? We do not want that. So are you adding some kind of checks in the J2 to ensure it's integrated only if P4 is compiled?
Yes. Right now it is not there, but we already kind of have that in consideration. So we will probably add some feature tags and make sure that it's installed only for the scenario when the P4 Docker is basically present.
Okay, sure. Thank you.
So, Kishan, a quick question on this vendor kernel module. So I see that there is this bubble which essentially, redirects the packet to, P4RT kernel module to add some of this metadata.
Mm-hmm.
So is that modification into the kernel module? How do you really, where is that code which essentially redirects the packet to the P4RT kernel module?
So this is a new kernel module, right? So if we require this this special handling for the P4 runtime packets, then we expect that this kernel module is kind of installed when the system comes up. And the vendor kernel module can basically look at the packet metadata, and if it finds that it matches these the user-defined traps, then it basically have to call into this new module to. There are some the functions to basically send the packet out. So it basically will call that send function from that particular module and then send the packet.
But that's exactly my point, is that today's vendor kernel module does not have that support. So are you expecting that those to be modified by
Yes.
the vendor kernel module?
Yeah, exactly. So today, the vendor modules should have support for the host interface type gNetlink, right? Whatever their mechanism, they could basically use some filters on the packets to basically identify whether the packet belongs to the regular NetDev port or whether these belong to SFlow kind of packets which use the host interface type gNetlink. So based on whatever the vendor has done for the SFlow, it basically has to basically modify or extend on top of that to add the P4RT type.
Okay, thanks.
So those are the two changes that are required on the receive path, and we can go on to the transmit path. So the transmit path, as I briefly alluded to, it's pretty straightforward in the sense that for the first type of packets, which is the directed transmit, we know the exact port on which we want to send, and we basically create a socket from the app and then write into the corresponding NetDev port, and then the packet goes out. And for the second type, which is basically the submit to ingress, we require basically what is the name of the NetDev port name that is again specified in the cop.config JSON file. And cop.arc, basically when it parses this file, it basically identifies this, and then it basically creates the host interface with the CPU port. So generally we create the host interface port with the physical port, with the VLAN, or the lag port. So in this case, it creates the host interface port with the CPU port as the object ID, and that essentially will create the NetDev socket in Linux. So the only additional work that is needed from the vendor to support this is to basically extend their implementation of the current host interface port API to also support a physical port. Sorry, to also support a CPU port. So that is there is no change in the API definition or anything. It's just that the object ID for the port can also be a CPU port instead of the physical port. And of course, the vendor will also have to include some additional flags or any other additional things that might need, because the packets are now coming in on the CPU port in their switching pipeline. So in order to support that, if they need some additional flags, then even that support has to be done by the vendor. So given that, I think we can quickly run over the flows here. So during the system initialization, we have the regular NetDev ports created, and then we have the gNetlink modules inserted in the kernel, and Arc agent basically parses the cop config J2 file, and it tags the special attributes, and then it basically creates the gnetlink interface using the host interface type gnetlink API calls. And then so now it also creates the user defined traps for each of the CPU queues, and it now has a map of all the user defined trap OIDs to use for each specific CPU queue. And then when P4 runtime sends a request to create a particular flow, Arc agent basically picks up um, the CPU queue, and it basically picks up the corresponding user defined trap and then programs the ASIC, right? So that goes all the way to the hardware. And then let's assume some packets come and hit the ASIC, and then they are identified for punt. So the ASIC driver gets it. The hardware also basically puts the packet metadata with the specific context value that was provided. And the kernel module basically looks it up and then sends it out on the gnetlink socket, and then P4 runtime picks it up. So I forgot to mention that in the as a complement to the kernel module that we wrote for the generic packet send, we also have a user-defined packet receive module that sits in the P4 runtime application. So it's a library that can be reused for other applications if needed in the future. But that library essentially understands the packet attributes. It's basically a complement to the kernel module that it has to now identify how to decode the packet. And then the packet is decoded, and then the application gets it. And packet out is straightforward. If it's a directed port, it writes into the specific netdev port. And if it's a submit to ingress, then it writes into the submit to ingress socket. So yeah, I think that kind of covers it end to end. Any questions?
In the transmit location, you said you will put it onto the CPU port, and and how things are happening. Like you need to have a special handling in the SI to again push it to the hardware, or I didn't quite get that point.
So it's very similar to how regular NetDev ports are created, right? Like host interface for the regular NetDev port. So whatever code the vendor has for creating the host interfaces for the regular physical ports, it has to extend that implementation to also create a NetDev port for the CPU port.
Mm-hmm.
Right. So once that is created, whatever packets are basically written into that socket will arrive on the CPU port for the ASIC.
Okay.
Right. It's as though you're kind of injecting the packet into the CPU port of the switch. And after that, it basically just follows the switching pipeline.
Okay. And the CPU port will be created in the kernel as well, right? There will be the CPU port will be visible. Am I right or no?
Yeah, it will be visible in Linux, just like how Ethernet 0.
But and you will use it or no? You don't use it.
Well,
I mean,
the application is creating a socket on that NetDev port, right? And then it basically writes into that socket when a packet is destined for submit to ingress.
Okay, all right. And also, you mentioned in the beginning that so you will get the egress port also when you trap the packet to CPU. You will get there are cases where you need the possible egress port also, right? I mean, what is the application and how do we use it? I don't see any details for that, but
we have some specific scenarios. Like one common example is like traceroute. So in traceroute, every op you also need the packet is copied to CPU, and you also need which port the packet would have gone out, right? So that's a common example where the target egress port is used.
okay. But in case of router port, right, router interface, right, it can be on a VLAN or something. The actual physical port could be one of the member of the VLAN, right? I mean, would that be like I don't know, or what use case are we? I mean, with respect to router interface, I mean, is it always be physical or like can be port channel or VLAN? What? Oh, what exactly?
Most of the times, it will be a physical port that is of interest.
Okay. All right. Okay. If there are other port channel or VLAN, I don't know how to handle it, but okay.
Yeah, and I think typically, it depends at which stage the packet got copied. Like sometimes even the destination port decision would have already been taken, and the packet metadata would already have that information, right? And like for example, if it's a lag port, like maybe the physical port has already been decided and it already has the particular port, and the application just gets the actual port on which it went. But yeah, I agree. In some scenarios, it might not be true, and you will have the logical port rather than the actual port.
Okay. So when you push the packet on the egress port, right? So you will basically modify the packets like as if the hardware forwarding, right? You will update the headers and stuff like that, and then you will push into the egress port. And that case, there is a possibility that the hardware might say you drop this particular packet, but you might end up sending it out on the egress port. So the controller has to have a good knowledge on how things are working in the hardware, and then need to push it to the egress port. Correct?
Sorry, I didn't get that
So
completely.
when you write the packet onto the egress port, right, wherein you bypass all the validation and checks, right?
Is this for like the
Transmit
packet out
packet
on
out,
the
correct.
specific egress port, right?
Correct.
Yeah. Mm-hmm.
So here you are basically bypassing all the hardware checks, right? And so the controller takes care of modifying the packet and stuff like that, right? And
No, this is regular way in which SONiC uses for like sending packets out, right?
mhm,
Like you basically frame the packet in terms of the payload and everything,
mhm.
and then you write that into the socket. And then since the host interface was created by the vendor module basically knows what is the specific hardware headers and other things that it has to put in order to send. What we
Right. I
frame
mean,
is just the packet payload.
yeah. So that is the case where the Linux networking also come into picture, right? Basically, the lot of stuffs are being validated in the Linux networking stack, and then it basically push into the host interface. But whereas here, I don't think the kernel networking stack is involved, right? Anything for
Yeah,
forwarding.
kernel networking stack is not involved, but other applications also, like for example, let's take LACP, right? So even
Right.
LACP is basically just creating a socket and then writing the packet on to that socket. Right?
Yeah, I mean L2 protocols I understand, but for the
Mhm.
packet that we are sending could be L3 with the IP address and stuff like that. So that's something
Well,
controller will okay.
even in terms of the packet payload, we have to make
Mhm.
sure that from L2 header the packet is complete, right? Like we have
Right.
already decided that this is the port on which the packet has to go. So there is no route lookup or anything on the
Nothing.
Linux side that is required. So
Okay.
all that information is already resolved.
Okay.
Yep.
Yeah, thanks, Krish.
I think, yeah, thank you. I think we can go on to the next presentation.
Just a quick question. So what if DPDK enabled NIC with all your scenario? Is that there's no conflict in case of DPDK enabled NIC?
Is this about packet out or packet in?
Pack it in, pack it out altogether. You are simply snatching the net link, the people module here, kernel module, right? But the DPDK gets in, then there are some flows might be the same as you expected, right?
So,
I mean, yeah. So I mean, you may want to take a look from the DPDK possibly or BPV context.
yeah, we have not right now taken that into consideration, Kwan. I think we can kind of reach out to you to get more details. But yeah, right now we don't have that capability.
Okay. Yeah.
Okay. Thank you. I think we can move on to the next presentation.
Yeah, just a quick time check. We have 6 minutes left now. Will that be sufficient, or do we need to book another session?
I think I can hit the high points. I envision this being a pretty short one.
Okay,
Unless,
sure.
okay, something different.
We can go.
I agree. I think this the P4 is more of an informational thing about P4, and there are only a few points. It's a smaller HLD, so we can start and see where we go.
Fair enough. Rob, are you going to be the presenter?
Yes, please.
Thank you. Can you try?
Yes.
Great. You can see it. Thank you.
Okay, cool. So just rehashing some things that we've said in other HLDs. P4 is basically an open standard that lets us define or lets us define the switch behavior in a programmatical way. So as part of this, since we're introducing P4, we will also be providing a P4 program that leverages a lot of these features that we've kind of been talking about. Going through quickly. So I guess the way that you can think about the P4 program today, if you were to go into Psi, you have these behavioral models, which are these pictures kind of describing the pipeline, figurative or with figures. The P4 program gives us an explicit definition, and you can define the different parts of the program. So where that comes into play in Psi is that we have certain components that are fixed. So think like L3 routing, tunnel encapsulation, things like that. That's things that you can describe in P4, but you can also describe some of these configurable components. So ACLs, where you have certain matchers and qualifiers based on your policy, and then they can apply certain actions, but at different stages in the pipeline, you have different configurations for these types of things. And I believe we are still going to have a later HLD for Psi extensions, so I'm going to kind of leave that as a separate topic from this quick little talk. But yeah, so that's pretty much what P4 does. It just takes those object models, pictures, and describes them as a program. This buys us a couple of things, I think. One being P4 already has a community. There's already software simulations and things like that that can consume these P4 programs and basically give you a software simulation so you can compare that simulation against the actual switch, and like you get that level of confidence that what is happening in both places is the same, so things are likely going correctly. Because it's now a program and not images, you can write tools around it. So automated testing, fuzzers, things like that. You write the program, they automatically generate flows that can be programmed. They can do standard things that you would expect. So they can do strange things that you wouldn't expect, and like little errors can pop out because of that. But yeah, so like that is pretty much the P4 program. What this looks like when we will be submitting the code. So taking routing as an example here, you have these individual elements. These would basically be tables in the P4 program. We're just going to provide route in this document, but the program will cover all of them. So say you have a IPv4 route. You would define it as a table. It matches on this VRF ID. So as part of your keys, you have VRF ID, destination address, basically one-to-one mapping there. You have various actions that you can do on this, which would be like setting the next hop ID. So you go onto the next hop table. You can set a WCMP group, which then in itself would point to multiple next hop IDs, things like that. For the fixed components, they will pretty much look like this. They're just a pure P4 description of the tables. You can think of these as being reusable even across other P4 programs that we write against the SONiC switch. Moving on quickly to the configurable components. So ACLs being the example. Because they're configurable, we need to provide some information about the SI attributes that they point to. So you will see these P4 attributes for like the ACL stage. So in this case, ingress, but you could have pre-ingress or egress just as easily. And on this ACL ingress table, we're providing matching for 3 fields. The IPv4 source address, mapping to the SI field source IP, the base protocol from the IP, ingress, and the ingress port. So you have these mappings, and then the P4 runtime app basically will consume these, pass them down to the ORC agent, they'll realize the ACL tables, and then you can start programming against them. You can define actions. Here we just have a simple one, forward, drop, but you can think of it as other things, modifying header fields and things like that, changing IP addresses, etc., VRFs, things like that. And that's pretty much the real quick explanation of this. Going over the advantages one more time. So once you have a P4 program that defines the SONiC switch, you basically have this unambiguous machine readable code that you get to pass down to the switch to realize, but then you can also pass that exact same code to other tools. Helps you verify things, so you get automated validation from it. It essentially acts as a living document, so you have this program that as you add new features, you update the program and people can just go in, read it, see what's happening with it. And familiar interfaces, so there's already a P4 community that are very used to using these the outputs from the P4 tools. P4 info are things that we've kind of talked about, but even things beyond that. And then rapid innovation, this comes into play a little bit more with the P4 extensions, where vendors have the option to rapidly prototype basically their extensions and then slowly bring that to the community as official features. So yeah, squeeze that all kind of in. Any questions on that? I know I said it kind of quick. Okay.
So, Robert, I have a quick question on this one. So, apparently, looks like you guys have defined the psi.p4 for the behavior of the logical pipeline. So, you talked about this testing, right? So, do you want to just elaborate a little bit more in terms of, what simulation testing and what automated testing you have done, especially with the fuzzers and so forth, to ensure that, okay, this is achieving the same behavior that you expected?
Sure. So I'm not sure how much we're bringing out for the version 1 of this. This was more the program. But if you go and look at the P4 community, you have this behavioral model, which is like a software-defined version of the switch. So that software model will basically consume the P4 program and realize that as a software data plane. You can then generate packets and send them in. And in a testing environment, you should be able to send those same exact packets into the physical switch and basically get them out. and then you can basically do your verifications like that. Bhagat, correct me if I'm wrong, but I believe as part of V1, we're not bringing out a lot of testing in the bigger ones.
That's right. So the end-to-end and simulation testing need additional capabilities for the test runnability framework also. So we are releasing the pins work in stages. So for this release, for this SONiC release, the end-to-end testing and comparing with simulation is not part of the plan, right? So we would be releasing that in the next version. So that's coming out in the next version. But today, in-house, we have the capability to run all of these tests in simulation and compare it to the real hardware. And you also have the capability to run, replay tests, run fuzzing tests, and all that. So we do all of that today, and we'd like to export them to the community as well, and make sure that all of that is open source as well. It's just that the amount of work that is quite large, so we are doing it in a series of releases. So it's coming up in the next SONiC community release. Does that answer your question, Hari?
Yeah, it does. Thanks a lot, Bhagat. I think this is, my, I guess, inclination of asking this question was essentially also to understand as people try to probably add some extension, right?
Mm-hmm.
And once they do that, is there a readily available setup in which they can actually validate and also test it to make sure that, okay, first they have not broken anything that was already working, and then also validate whether or not what they have added, it works. So if there is something that can be contributed by, Google when they're doing all of this thing, that can certainly help the community.
Absolutely. We believe a lot in testing and validation and having a strong framework. So we do have plans to upstream this and make sure that everybody in the community can run these tests. Absolutely.
Yeah, but as part of this release, where you're not actually contributing back the test framework or tests and so forth, but at least I expect that you are going to be at least submitting the results of the testing, right? To show that, okay, what works or what is still to be done and so forth, right?
Yes, of course. Yes, we can release results of the testing. We would also, I also wanted to make sure that we are all on the same page in terms of what testing is covered and what testing is not covered. So there is a lot of unit testing, component testing that is coming in along with the initial release itself. It's the end-to-end and comparison with the simulation test. That is the part that needs the framework, and that's coming in the successive release. But we are happy to release the results of the testing. What are the tests we are running internally, and how they look, and all of that. We can definitely export that as well.
Yeah, thanks, Bhagat.
All right, we are 7 minutes over. Any last minute comments, questions? If not, thank you so much for presenting Google, and thank you very much for everyone joining today's HLD review. Thanks for the questions.
Thanks,
Have a
everyone.
good one.
Thank you, everyone.
Thank you all.